Good morning, students. Myself, Vaidegi, working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today, the video lecture is from the subject EC3452 EMF. Today, the discussion of topic from the Unit 3 Magnetostatics. In this lecture, we will study the magnetostatic, which deals with magnetic fields produced by the steady currents. We will learn how to calculate magnetic field intensity for different current distributions, understand magnetic circuits, and explore the behavior of magnetic materials. These concepts are fundamental for understanding transformers, motors, generators, and many other electromagnetic devices. The course outcomes are, by the end of this lecture, you should be able to calculate the magnetic field intensity for various conductor configurations, analyze magnetic circuits using magnetic circuit concepts, understand the behavior of different magnetic materials, and apply these principles in practical engineering systems. First, we see about the introduction to magnetostatics. Magnetostatics is the branch of electromagnetics that deals with magnetic fields generated by constant or steady currents. Since the current does not vary with time, the magnetic field also remains constant. The important quantities used in magnetostatics are magnetic flux density B, magnetic field intensity H, permeability, magnetic flux, electromotive force. These quantities help us describe and analyze magnetic fields and magnetic circuits. First, we see about the magnetic field intensity. Magnetic field intensity represents the magnetizing force that produces magnetic flux in a medium. For a magnetic circuit, H is equal to Ni by I, where N is the number of turns, I is the current, and L is the magnetic path length. The unit of magnetic field intensity is ampere per meter. A high current or greater number of turns produces a stronger magnetic field. Next, we see about the field due to the long straight conductor. When current flows through a straight conductor, a magnetic field is produced around it. The magnetic field intensity is a distance r from the conductor is given by H is equal to I by 2 pi r. Notice that the field intensity decreases as the distance from the conductor increases. The direction of the magnetic field can be determined using the right hand thumb rule. If the thumb points in the direction of current, the curled fingers indicates the magnetic field direction. The field due to the circular current loop. A circular loop carrying currents also produces a magnetic field. At the center of the loop, H is equal to I by 2r, where r is the radius of the loop. The magnetic field lines are concentrated near the center of the loop, making this arrangement useful in electromagnetic devices and sensors. Increases the current, increases the field strength. Next, we see about the field due to the solenoid. A solenoid is a long coil consisting of many turns of wire. The magnetic field inside a solenoid is nearly uniform and is given by H is equal to Ni by L. The field strength increases with the number of turns and current. Because of its strong and uniform magnetic field, a solenoid is often used in relays, actuators, and electromagnets. Next, we see about the field due to the toroid. A toroid is a circular ring-shaped coil. The magnetic field intensity in a toroid is H is equal to Ni by 2 pi r. An important advantage of a toroid is that the magnetic field remains confined within the core. This reduces the magnetic leakage and improves efficiency. Toroids are commonly used in transformers and inductors. Next, we see about the magnetic circuits. A magnetic circuit provides a closed path for magnetic flux. Similarly to how an electric circuit provides a path for electric circuit. Examples include transformer cores, motor cores, and electromagnets. Magnetic circuits help us analyze magnetic flux flow in a systematic manner and simplifies the design of electromagnetic devices. Next, we see about the magnetic circuit parameters. The important parameters of a magnetic circuit are magnetomotive force or MMF. MMF is equal to Ni. Magnetic flux pi is equal to MMF by reluctance. Reluctance R is equal to L by nu A. Reluctance represents opposition of magnetic flux just as resistance opposes electric current. materials and allows magnetic flux to pass more easily. Next we see about the electrical versus magnetic circuits. There is a strong analogy between electrical and magnetic circuits. In electrical circuits, the voltage drives current, resistance opposes current. In magnetic circuits, the mmf derives magnetic flux. Reluctance opposes magnetic flux. Understanding this analogy helps us analyze magnetic circuits using concepts already familiar from electrical circuit theory. Next we see about the magnetic materials. Different materials respond differently when placed in a magnetic field. This behavior depends on the arrangement of electrons within the atoms of the material. Based on their response, materials are classified into three main categories: diamagnetic materials, paramagnetic materials, ferromagnetic materials. These materials have different permeability values and magnetic properties. First we see about the diamagnetic materials. Diamagnetic materials are weakly repelled by magnetic fields. They have relative permeability slightly less than 1. Examples include copper, silver, bismuth. These materials do not retain magnetism and are generally considered non-magnetic in engineering applications. Next we see about the paramagnetic materials. Paramagnetic materials are weakly attracted by magnetic fields. Their relative permeability is slightly greater than 1. Examples include aluminum, platinum. The magnetic effect is very small and disappears when the external magnetic field is removed. Next we see about the ferromagnetic materials. Ferromagnetic materials are strongly attracted by magnetic fields and can retain magnetism even after the external field is removed. The examples include iron, nickel, cobalt. These materials are widely used in transformer cores, motors, generators, and magnetic storage devices because of their high permeability. Next we see about the BH curve. The BH curve shows the relationship between magnetic flux density B and magnetic field intensity H. As H increases, B also increases until the material reaches saturation. The BH curve helps engineers select suitable magnetic materials for different applications. It is particularly important in transformer and motor design. Next we see about the hysteresis. Hysteresis refers to the lagging of magnetic flux density behind the magnetizing force when a material undergoes repeated magnetization cycles. This lag produces energy loss known as hysteresis loss. To reduce hysteresis loss, transformer cores are made from materials with narrow hysteresis loops. Next we see about the applications. The concepts discussed in this lecture are applied in transformers, electric motors, generators, relays, magnetic sensors, hard disk drives, magnetic memory devices. Understanding magnetic field intensity and magnetic materials is essential for designing efficient electromagnetic systems. Finally, we came to the summary of this lecture. In this lecture, we studied magnetic field intensity, magnetic fields due to various current distributions, solenoids and toroids, magnetic circuits and their parameters, comparison between electrical and magnetic circuits, diamagnetic, paramagnetic and ferromagnetic materials, BH curves and hysteresis. These concepts form the foundation for the analysis and design of electromagnetic devices. Thank you for the attention.